we'll start from current slide, which is just a blank slide. Here are a few announcements, and there's more than just a couple. Let's think which one's the most important. Probably this one is the most crucial. Next Wednesday, somebody in Montgomery came up with the brilliant idea that all full-time instructors have to go down to Montgomery for a professional development day. Sounds like to me a enormous waste of time, energy, money, and opportunity. Okay? It sounds terrible, but we're required to go. Now, the meeting is supposed to be over in Montgomery. Somebody told me this, so I don't know exactly. They said 3 to 3:15, something like that. So what I'm planning to do, there is a bus running from both campuses, but what I'm planning to do, and we can drive if we want to, so I'm going to drive there and then try to leave maybe a little early so I can be back here for the 4:30 class. Okay? Now, because we only meet once a week, that's a whole week's of material we're missing if I don't do that.
You gotta do all that.
Well, we're not going to get the material covered. Okay, well, what we could do is wherever we end this week, then you'll need to pick up the video I made last time I taught the course and use that video for next week, and then I'll pick up from where that video ends and start the next week. Do you want to do that rather than meeting?
I mean, that's a long drive.
Well, I'm going to have to drive back anyway. Yeah, but I mean, I've got to drive back anyway. I mean, huh? Okay, I can. Okay, so y'all don't want to meet next week in person. See, on the video, you don't get to ask questions. You don't say, can you do this problem? Can you do this? So if you're okay with it, we'll just, at the end of class today, then I'll let you know what video to watch. And I'll actually show it to you, which video to watch. And then at the end of that one, that's where we'll pick up in 2 weeks. You okay with that? Okay. So, therefore, I won't be. Okay. Yeah.
You heard about the meeting they had next week.
All righty.
What kind of meeting? All the professors here have to go to a meeting Wednesday, and they have no choice. So.
Okay.
Oh, okay. Next Wednesday.
Next Wednesday, we have a required meeting in Montgomery for no apparent reason at all, except just force us to do it. To go down there, spend the whole day, and then come back. And so.
Buses going, but he was going to drive himself so he could be back by
4:30. I think I can do it. I might be a little late depending on how traffic is, but I can do it.
I feel like he need to ride that bus.
Yeah, I won't get back in time for the bus if I ride the bus. Because you see, from what I understand, the last meetings are going to be scattered all over Alabama State campus, and then they got to get all the shuttle buses back to the stadium parking, and then we load up on our buses and come back. So it's a pain in the neck. So a lot of people are driving just because they don't want to go through that. But we just told those two guys that we're not having class because that's what the four of you said. So what we'll do at the end of class today, I'll end the recording, and then I'll go to the YouTube video and show you where to pick up. It may not fit exactly, but it'll be the closest we can do. And then you'll have to watch those videos, 1 or 2 videos, depending on where we end today. And then we'll pick up at the end of the next video, and that's where we'll pick up in 2 weeks. Yeah, today's the 2nd, next week's today's the 3rd, next week's the 10th, and the following week is the 17th. So we'll be back here the 17th. We'll have class on the 24th, and then that, I think, is our last class. Yeah. Yeah. Yeah, because final exams are the following week. But I'm going to give you your final exam that last time we meet. I'll be here for you to turn in those exams when you come back.
So we in chapter what, 17?
We're in 17, and we only...
3 more weeks of school left. We take out finals the first, second, and third. We're
Yeah.
gonna be short on something, right?
What's that?
We probably won't get to one of them tests, right?
Well, I don't know. We're going to get as far as we can tonight, and then the YouTube videos will be for next week, and then we have class but then on the 17th and the 24th. So we'll see how far we get. Okay. Now, even though we're not at the place for this video, I think I'm going to show it anyway because I don't know why. Well, I do know. So let me.
I do have a question, but I don't
Okay, yeah.
Should we wait till the end of class to do it?
No, this is a good time.
Well, it's about a homework problem.
Okay, this is a good time.
Okay.
Which one's that?
This is for chapter 16, but it's
Okay.
not one of the easy problems and stuff.
Okay, or odd problems.
Yeah.
Okay. Which one? What page? What that?
449.
449. Okay. That's not a 449. Oh, I'm 445. Okay, okay, got it. Okay.
And it's going to be number 12.
Number 12. All right. This is on page 449. Let me get my pen activated. Page 449. This is chapter 16, review problems. Yeah. Number 12. All right. A train traveling at a speed of 95 miles per hour. Okay. Now, if you look just across the page at that, your formulas, what we're using here is formula 16.4, because this is a Doppler effect, right? Yeah. So 16.4 is your formula. I'll put this here. 16.4 is the formula, and it's F prime.
Learn in here like the initial velocity is always 0, because that's like what?
Okay, that's okay. Okay, initial velocity isn't always 0, but quite often it is. If you were coming to a stop, you're traveling at 60 miles per hour, that might be your initial velocity. You got to stop when you get up here, so your final velocity is going to be 0. So in that case, your initial velocity is the higher speed. It could be 30 miles per hour, or 14 feet per second, or anything like that. Okay, if you started from rest, your initial velocity is 0. If you drop something, initial velocity is 0. But if you're moving and then coming to a stop, the initial velocity is whatever velocity it was at the beginning. That's what it means, initial. At the beginning of the problem, what is the velocity? Okay, now this is dealing with frequencies, and it's F prime is equal to F times V over V plus or minus Vs. I'm trying to get the same symbology they use in the book. Now, what are these things? This is what you might call, let me read it from the thing. I'm going to call it the Herd frequency. This is what you think you're hearing. This is what you're hearing, the Herd frequency. Okay? This is the actual frequency of the, what is this, a whistle, a horn, or whistle. Okay, the actual whistle frequency. Okay, the actual frequency of the whistle. This is the velocity of sound. This is the sound velocity. Velocity of sound, speed of sound, okay, which is the same as this one, okay, and this is the source velocity, velocity of the source. That means, in this case, it's the train, yeah, this source, which in this case is the train, okay? You understand what each of these things represent now? Okay, so A train traveling at a speed of 95 miles per hour. That's your V sub S. V sub S is 95 miles per hour. Already I can tell that may be an issue. Okay? Approaches an observer at a station and sounds a 525 hertz whistle. That's your actual whistle frequency. So your F is 525 hertz. 525 hertz. And by the way, that's a per second. We'll just leave it as hertz for now. Okay? What frequency will be heard by the observer? This is what we're looking for. This is the unknown. And that's exactly what we're going to calculate. Okay? Assume that the sound velocity in air is 1090 feet per second. So, I'm sorry. Put F because I've been writing F for everything. Okay, this is going to be your V, your speed of sound in air. We're going to assume to be 1090 feet per second.
So why do we have 95 kilometers now?
No, it's miles per hour.
Is it? Hold on, I'm sorry. Never mind. I was looking at the next one.
Okay, is this the one you wanted to have?
Yeah, that's the one.
Okay. All right. Yeah, the next one is 95 kilometers per hour. Yeah, it's funny they use the same. Okay. Now, you've just almost hit on the first issue here. The first issue is, here we have miles per hour. This is the same as per seconds, and this is in feet per second. Hey, these are not the same units. Okay, so what we have to do is get the 95 miles per hour into feet per second. Okay, now we can do it with the train track method, since this is a train problem, okay, but that's going to require us to know a few conversion factors, or we can turn to the back of the book and use their conversion factor. Which do you want to use?
Let's just use with the book now, 'cause that's
In the back of the book?
I'm going back, yeah.
Okay, so if you turn to the back of the book, all right, not the very back, but near the back, page 680, starting on 686, I don't think it's there. No, it's not. 687, conversion table for volume, no. Mass, no. Density, no. 688, time, no. Speed, that looks like the one we need. Okay, and we're trying to get from miles per hour to feet per second. So we're trying to get the feet per second. So 1 foot per second equals 0.682 miles per hour. Okay, that's one conversion. The other conversion will be, if you go the other way, miles per hour to feet per second, 1.47. I don't know which one you want to use. It doesn't really matter. Let's set up the train track anyway. Okay, this is going to be times blank blank is equal to blank, and we know we're trying to get to feet per second. Okay, now same as before, only this is only a one-step problem now. Put the units in their place. Remember, the first blank is for numbers. Leave that alone for now. Put the units into place. We want miles per hour either above or below the line and feet per second in the other position. Which goes where? Okay, if miles per hour is at the top, if you do that, then you have miles squared per hour squared, and you per foot per second. That's not going to work. You want feet per second on top. So let's not put it that way. Okay? You want to put, can't get my pen to work. Come on, there we go. You want feet per second up here, and you want miles per hour down here, so you can cancel them out. Okay? You want to be able to cancel out miles per hour and leave you feet per second just where you want it, right? Okay, now you've got a choice on numbers. Okay, how many feet per second is a mile per hour or vice versa? And in the back of your book, you see that 1 foot per second is 0.682 miles per hour. So you can either put the 1 on top, 1 foot per second is 0.682 miles per hour. You can do it that way, or you could have done it the other way, 1 mile per hour, put the 1 on the bottom, is 1.47 feet per second. So you can do it either way you want to. I chose to do it that way because it was the first one listed. Also, it's a little bit bigger number, so we might get a little bit of precision with it. But it does involve dividing. If I were doing this by hand, I'd definitely multiply. I'd do it the other way. But since you're probably using a calculator, calculators don't take any more time. So you take the 95, divide it by 0.682. It's going to be not quite double. I'm going to say about 175, 150, something like that. Oh, I'm sorry. Yeah, going that way. Say again, 130?
39.29, and then the last number is 6. So I don't know if you round it up.
Let's just make that a 3. 139.3. Okay? We don't need that many digits because we only have 2 here. You know, so that's going to be plenty of digits. All right, now we can plug in. We're looking for the f prime. So the f prime is equal to, I'm going to put it right here, the frequency, which is 525 hertz, okay, times the velocity of sound, 1090 feet per second, divided by velocity of sound is 1090 feet per second. Okay, plus or minus. Okay. Okay, wait, let's think about it now. The train is coming toward you. So that means the frequency is increasing. Now, to make the frequency increase, you make the denominator decrease. So you subtract the denominator. Now, you can go back in the text and see the same thing. And this is, yeah, oh, there it is. On page 4, I can't read it, 439, the plus sign in the denominator is used when the source is moving away from the observer. The minus sign is used when the source is moving toward the observer. So we use the minus sign because in this problem, the train is approaching the observer. So it's approaching. So we use the minus there, and we'll subtract what we just got. I think 139 is probably going to do enough for us because you only have 3 digits anyway. Okay, and that's also feet per second. Okay, now let me get.
Is physics basically taught the same everywhere? Because like for every problem we have, even the ones in the book, like it's a YouTube video about it. Like somebody that had the same exact problem.
Okay, I wasn't aware of that, but it's believable. As long, okay, every problem in this book has it. Is that what you're saying? Mm-hmm. Okay, it's this book specific, right? Yeah. Yeah, and so if that's the case, I can't say everyone teaches it the same way. Some people may want you to memorize formulas. Some people, yeah. Okay. Make sure I get your name right, though. Latondria, right? Yeah, okay, that's what I was going to say, but I wanted to make sure I had you. Okay. All right. I just got a new...
I tried this at home last night, and something just kept on, something wasn't coming out right when I kept calculating.
But it's coming out right now?
No,
let's try it.
If I'm doing like I'm putting the numbers here.
Okay, well, let's see. This is 500. I can't write. Okay. 525 hertz. Yuck. All right. 525 hertz times 1090 That's feet per second, divided by, when you subtract those two, you get 9, let's see, you'll be a 1 there, 5 there, 851? I don't know. Okay, feet per second. Let's see. Is that right? Okay. Now, so you do 525 times 1090, and notice here, your units here, these units cancel out, which is very good because you want the frequency to be in hertz.
Well, it's supposed to be 951, but
951?
You're doing the 1090 minus 139, right?
Yeah. You're right. You're right. That's 951. You're right. Sorry.
Okay, so
I was doing it in my head. Yeah. And what you got? So let's call it 602 hertz. You can't get more precision out of it than you put into it. So 602 hertz.
You know, at home what I was doing, I was calculating it all together. Calculating like the top one.
Yeah.
But it wasn't coming out right.
Okay. I'll tell you what I'm guessing happened there. Okay. Anytime you have a calculation that, say, a division here, if you don't put parentheses around this subtraction, remember, please excuse my dear Aunt Sally, it's going to divide before it subtracts. If you put the parentheses here, it subtracts first and then divides. So that's what my guess.
That's what I'm doing. Let's see. Okay.
Did you put parentheses?
Did
Okay.
you forget to change over the units? Because that's what I did. I plugged in the miles per hour.
95. That would give you a wrong answer.
No, I didn't do it.
You did get 139 or something like that. Okay. So here's what you type in. 525 times 1090.
Put the parentheses first?
You don't have to, but you could.
Okay, so I'm going to try with the
parentheses. You going to put the parentheses? Okay. 525 parentheses, or times parentheses, 1090 divided by, then you have to open another set of parentheses.
Oh, okay.
See, this has to be in parentheses, not these in its own parentheses. Because if you put just divided by this minus this, it's going to divide that, then subtract that from it. Yeah. That's why you have to put this denominator in its own parentheses.
Okay, I got it now.
All right, good deal.
I realized that I kept on coming up with a negative number.
Yeah, that would be a problem. Okay.
Okay, let me finish writing this down.
Okay. Glad you asked the question. That's a very common, and it's only a calculator error. It's not that the calculator made a mistake. It's doing what you tell it to. You just didn't tell it, do that first. Do the subtraction before you do the division. Because calculators are sort of dumb. They can't figure it out. Okay? You have to tell it exactly what to do. Okay.
Thank you.
All right. That's it for questions? All right. Then let's turn back to Chapter 17, where we left off last time, which was at the bottom of page 462. Yeah. Now, what I'm going to do for right now is get out of this slide. Hopefully we won't need it again. Is that the answer they had in the back? Oh, they don't have it in the back. Yeah, but that makes sense. It makes sense. It's a higher frequency because the train's coming toward you. All right. Now, I'm going to jump ahead to this slide, okay? Not because we need it right now. We're going to see this later. This is in a different section. But what I want to do is point some things out to you. We started this last time when we were talking about simple circuits. That's 17.5, okay? And then the subtopics here were first your source of energy. That's usually the battery or the plug in the wall or something like that. That's your source of energy. The second subtopic was your conductor. That's the wires, okay? Here are the wires. Those are the conductors. Now in your illustration, that's your source, that's the battery. The long line is on the positive side, the short line on the negative side, and we assume the current is going from plus to minus, even though electrons usually go the other way. But we'll make that assumption. Well, what we're doing tonight is starting with the third part here, the load. That's whatever is using the energy the battery is supplying, that the source is supplying. The source gives energy to the charges. The wiring conducts the charges, and the load uses the energy that the battery has given those charges. So that's the picture here. Tonight we're talking about the load. Okay? So, and I think I'll go on and write on this slide, even though this isn't the right place for it. Well, no. Okay. The next thing, and this is on this slide too, those are the three components. And all it says about the load is the load, in the load, the electrons lose the energy. The charges lose the energy that the battery provided. Okay? It converts the electrical energy into other forms of energy. That is light. So it would be light. Most light bulbs also get hot. Some of that energy goes to heat. You don't want it to, but it does anyway. Okay? It could be sound if it's a radio. It could be a picture if it's a television. It could be the AC system. Whatever is using the energy, that's the load. It could be changing to any other type of thing. Okay? And then they continue through the wire. The charges do. You don't use the charges. Use the energy the battery gave the charges. The charges keep on trucking. Okay? They get back to the battery. It boosts the energy again. That's the circuit. Okay. Now, the other part that's not a physical part, but is a part of it, is the current. And that's what I stands for, the current. That's the next thing that we're hitting here. What in the world is current? Okay? Current is the rate at which the charges are moving. So it's the time rate of change of the charges. So let me get my pen back. Okay, so current, the symbol for it is I, is equal to charge. The symbol for that is Q. I think this uses little q. I can't remember. I'm going to use little q for charge divided by time. Current is equal to charge per unit time. The units for current are amperes. Capital A, because it's named after Louis Ampere. We talked about him earlier in Ampere's law. Remember that? Amps is equal to coulombs, named after Charles Coulomb, also a Frenchman. That's the charge per unit time. That would be in seconds. So an amp is a coulomb per second. Current is charge per unit time, the time rate of using charge. Okay? Now, another thing that's on here, not really listed here, but it is here, whether you believe it or not. Let's go back to the source here. What the source is providing a potential difference. Remember we talked about potential energy, okay? Giving more energy to the charges coming out than what it was coming in, okay? So that is going to create a potential difference. A potential difference, the unit for that is voltage, okay? Now, it's not just energy. What potential difference is, and the symbol for that is capital V, okay? Or at least that's the one I use, okay? Some books use E for electromotive force, but I prefer V for now. There's a reason for that. So voltage is equal to the energy, and that's why I don't like to use E for voltage, because it's energy. They're calling it work, which is fine, work or energy, either one, per unit charge. That would be Q. Remember, the charge is Q. So the units for this, now this one, the unit for voltage is volts. So that's also capital V. The reason it's capitalized is named after Alessandro Volta. He's the one that basically developed many of the early batteries. Okay, he didn't discover it, but he developed it. Okay, he actually lived in Lake Como, Italy. Okay, and several years ago, my wife had professional meetings in Lake Como, Italy, and it was the week in between terms. I got to go. Okay, she was in meetings. I got to view the city. We happened to take our niece with us, her niece actually, and so this was several years before she was married, and she now has 2 kids. So this was several years ago, but Julie and I got to walk around the city and see things, and there's this beautiful, right near the lake, beautiful little gazebo type area, just really pretty. So I said, let's go see what that is. Julie said, yeah, it looks really nice. So we walked up to it. It was basically a museum or a monument to Alessandro Volta. I didn't know he was from Lake Como. We went in there and saw behind the glass many of his early batteries that he put together, the different materials he used, and some of his handwritten books, where he recorded. We got to see Alessandro Volta's hometown, and that was almost the epic of the trip. A little bit better was going to Switzerland, which was not far away, and getting Swiss chocolate. That was a little bit better, but not much. Okay. All right. Besides, my wife said we had to. Okay. So the unit for volts is also V, capital V for volts, named after Volta. And that is the unit for energy or work is joule, and for charge is coulomb. All 3 named after people. Volta, volts after Volta, joule after James Prescott Joule, and coulomb after Charles Coulomb. Okay? A Italian, English, and a Frenchman. So very international. Okay. So that's why we measure the energy per unit charge or voltage given to the charges that run around the circuit. All right? Well, obviously something else is at play here. Something has to use that energy. Well, we know it's a load, right? Well, what is it that uses the energy? Something has to resist the movement of those charges, and that is called resistance. Okay? That would kind of be like, the water towers, they pump water up to the tower. That gives potential energy to the water. So when you use water, you don't have to pressurize the water. It has it because of that potential energy up there. So that's sort of like the voltage. The pumps pump it up. That's giving energy to the water. Now, if you are using that water and you're just running water on your plants, that's fine. It just comes out. Not a lot of resistance there, but a little bit. But if you wanted to squirt your little brother, you put your finger over and offer more resistance. Now the water, not as much comes up, but it comes out faster. Okay? That's providing resistance. Not that you would ever do that. But anyway, that would be resistance. That's what we're talking about here. What is it about the load that makes the light come on? The fact that there's resistance there. The resistance produces heat. The heat heats up the filament until it glows. That's what gives you light. Now that's in the old kind of lights, the incandescent lights. You actually heat a filament until it's hot enough to make it glow. That's why those light bulbs get so hot. Now different things are happening in fluorescent bulbs. Okay, that's a different issue. What's that? No, it's not really a liquid. It's a mercury vapor, so you might think of it as liquid, but it's actually a mercury vapor, and you have a large potential difference caused by your power source, actually in a capacitor, which builds up even more of it, and that high voltage that you have there sends ions flying down the tubes, and when they fly past the phosphorescent material, which is that white powder, if you've ever seen a broken tube, you know it's coated with that white powder. That's the phosphorescent material. When those high energy electrons go down, the electrons that are in that phosphorescent material, they jump up an energy level, okay? And then when the high energy electron passes, then they fall back down. When they fall down, they produce a photon of light. So that's how these work. very little resistance. So these don't get nearly as hot as an incandescent bulb. Now, a lot of projectors these days, now some of these do get hot. The old ones that were actually, see, that's not very hot at all. The old ones that were actually filaments in there, those got really hot and they burned out really quickly. These are now, I think, LED projector. Okay, what that is a light-emitting diode. A diode sends current in one direction but doesn't let it go the other direction, and when it goes through, it produces a certain wavelength of light. And physicists probably, I don't know how many, 20, 25 years ago, came out, well, maybe even longer than that, with a red LED. Only produced pure red light, okay? Well, that was great for Christmas lights or things like that, but not really for much else. And then, within a few years, they came out with a green light, a green LED. Well, that was, again, very nice for Christmas, but not for very much else. Well, maybe stoplights, but I don't think they really used them there. But then, and this has only been in the last probably 10 or 15 years, finally somebody came up with a blue LED. So now they put all three of them there, and when you mix red light and green light and blue light, you get white light. And according to how much, whether you put a stronger blue or a stronger green starter, you can change the quality of the light. Like this is a very bright white, which is probably a little more blue and less red and green, whereas sort of a softer one may have a little more red and a little less blue and green. So you can adjust the quality of the light by what power of LEDs you put in there. Those LEDs are very energy efficient. They last a long, long time. They take much less energy to produce the same amount of light. So you'll see on the light bulbs that are LED bulbs, they'll say 75 equivalent, but they're only 6.3 or something like that. 75 watts equivalent to an incandescent bulb, but it only really uses 6.3 watts. Very much less power to get the same amount of light. So that's why they're the things to go to. They're a little more expensive, but they last a long, long time, much longer than incandescents. So I don't know if they got the cost down so they're equivalent, but it certainly is a lot more energy efficient. Okay, so that's beside the point. We're talking about resistance, and the opposition to current flow is called resistance. Okay, so let me go back to the other slide, and we'll talk a little bit more about resistance. Well, there we go. All right, I'll have to get my pen color back. Okay. So again, resistance. Okay. The definition they give here, a pretty simple one, the opposition to current flow. Okay. Are y'all real football keen people? You're not. Oh, shucks. There went that illustration. Okay. Okay. How about traffic? You deal with traffic. Okay. What if, and this happened, when was it? Sometime recently when we were driving. I can't remember if there was an accident. I think it was. I think it was an accident. And where you had, say, 3 or 4 lanes of traffic, suddenly you had one because the accident took up 2 lanes over here. Well, that resists the traffic flow. Now people have to get in behind each other and stuff, and everything slows down. So that's opposition to the flow of traffic. Well, resistance in your current... Right. So this is the opposition to current flow. It's a lot like the wreck on the highway. So their resistance is determined by several factors. Here are 4 of these. Okay? One factor, and this is in reverse order of what I usually do, most books teach, but is temperature. Okay? Now, the increase in temperature as the T goes up results in the resistance going up. Okay? And that kind of makes sense, because if you think about it, as the temperature goes up, okay, the molecules are bouncing around faster, okay? Whatever it is, the electrons, the molecules, whatever, they're bouncing around faster, bumping into each other harder, creating more resistance to the flow, okay? So the higher the temperature, the higher the resistance, okay? Number 2, the length of the wire, okay? Now, let me give you a dumb example for that. Several years ago, the length of the wire, or the length of the conductor, offers the longer the length, the more the resistance you got. And here's this. I don't know if this has ever happened to you. Many years ago, we had, over in Georgia, there was a really bad ice storm. And we had just fairly recently built our little 2-bedroom bungalow over there, so when we went over to the farm, we had a place to stay. We didn't have to bump in with my brothers or their families and stuff, especially if they had their families there. We'd like to see their families, but if we went at the same time, there wasn't room for us to stay, okay? So we decided to go and build a place on the farm, part of that I inherited when my parents died. So we did, and we thought it'd make the land more valuable later, you know, and stuff. So there were several reasons. So we built this little thing. Well, we had 4 big old pecan trees, not really close to the house, but out between us and the road. And that ice storm, oh man, it broke huge limbs and small limbs, all kinds of limbs out of that those pecan trees. Well, I went over sometime or another after the ice storm, probably the week of spring break or something, and my brothers and I, you know, we got out there with chainsaws, and the big pieces we hauled off and dumped, and the little pieces we just left and we were going to burn later. So we stacked those up. Well, it was probably a later visit when we went. It had dried out some, you know, the wood had dried out, so it burned a little better. So we were going to start a fire with this and burn this pile of thing. So we ran our hoses down from the house. So the house sits way back here, and this first tree we're going to do is one furthest away. So I ran all the hoses we could, one after another, to reach down to the thing. Still didn't get quite close enough, but got there. But when we turned on the water up here, what came out down here was just, you know, whereas up at the house with just one hose on it, it came out really well. But down here, after maybe 4 hoses in a row, it went, you know, so you couldn't really do much at all with that except fill up buckets and stuff. It wasn't the best situation. Why? Because the longer the hose, the more resistant to the flow of water. Makes sense, doesn't it? Because those sides of the hose are all slowing down the water, okay? So by the time it got after 4 or 5 hoses, it was just dribbling out.
There's really no force behind water, is it?
Yeah, well, the thing is, it was the same pressure, but it had so much resistance that the water coming out didn't have much energy left, okay? Now, same thing with a wire or any conductor, especially if it's a good resistor. The longer it is, the more resistance it has, okay? So that's the other thing, length. And again, the longer the length, the more the resistance, okay? The longer length produces more resistance, okay? If we double the length of a given wire, the resistance is doubled, okay? The third issue, cross-sectional area. Okay, what in the world do we mean by that? Remember when you were going to squirt your little brother? Okay, you decreased the area that was coming out. That offered more resistance to the flow of water. So even though it came out stronger, actually less water came out. Okay, so when you increase the cross-sectional area, you also increase the resistance. Okay, Resistance varies inverse. Whoa. No, I'm sorry, I said it backwards. When you decrease the cross-sectional area, when you made the area smaller. Duh. Okay. When you decrease the cross-sectional area, you increase the resistance. Yeah. And you increase the cross-sectional area, you decrease the resistance. So that's an inverse relationship. Number 4, the material. Okay? The material varies by conductivity, and we talked about that a little bit maybe, I don't remember. The best, very best conductor out there of most materials is silver. But silver is awfully expensive. Just slightly more resistant, but not much, to silver is copper. Copper is much cheaper than silver, and also it's much more flexible. If this was a silver wire, I'd be out of here. No, I mean, if this is a silver wire, I probably wouldn't be able to bend it as easily because silver is sort of stiff. Copper is pretty, there is a word for it. I can't think of what it is now. So the material, okay? So let's think about that light bulb, okay? Have you ever really looked at the filament in an incandescent light bulb, especially those bulbs that are clear and you can see the filament in there? Now, what did you notice about the filament?
We got like a little bridge.
Okay, yeah, the little bridge there. I'm talking about the filament between the bridge.
Spring?
Yeah, it looks like a spring, doesn't it? What has that done? They've taken that filament and then done it in little coils like this. And you go round and round and round and finally do. If you were to stretch that out, that'd probably be, rather than this long in the coil, it'd be at least that long. So what have you done? You increase the length, you've increased the resistance. Okay, there's the increase of length. What else you noticed about that filament? Big old fat wire in there?
I know when it's bust, that little bridge thing gone. Like when the black bulb don't work.
Okay. Okay, we'll talk about that a little bit later, but what do you notice about the filament? Is it a big, thick, heavy wire? No! It's really about maybe a little thicker than a hair. Well, if you had hair. Well, never mind. Okay. But it's very thin wire. So it has a very small cross-sectional area. There goes the resistance up again. Okay? And the other thing is the material. That's not copper wire. When Thomas Edison was developing the light bulbs, it took him a long time and many, many materials he was testing, and he found out the best material was one called tungsten. Okay, tungsten, you could heat it up. It had a lot of resistance, so it heated up quickly. It glowed a really nice, bright white light, and it didn't burn out very frequently. It did burn out, but it wouldn't burn out frequently. So there's the material. If he'd have done copper wire, not good light at all. It probably would take a lot of energy to heat it up because it has a good conductor. But you see, tungsten was a poor conductor, so it heated up. Okay. Now, let's talk about temperature. That's the only thing we haven't mentioned. Most of the time, when those incandescent light bulbs blow out, when do they go out? Have you ever noticed? When you turn it on. Now, why in the world would that be? Well, because when you turn it on, the wire is cold. And when it's cold, it's a better conductor, less resistance, so more current flows through it. And if the wire has gotten really thin and weak and more current goes through it, it blows. Yeah, exactly. Once it gets hot, then there's more resistance and it doesn't send as much current through, so it not as likely to blow the bulb. That's why. Because resistance depends on temperature. And when it was low resistance, more current flowed through, and that's what blew the bulb. Okay? So we've seen illustrations of all of those. Okay? Oh, and Alessandro Volta is mentioned on page 463. Little blurb, not much on him, but a little bit. All right. So let's do example. Before we do, the formula that relates all these together is R that's resistance, okay, is equal to rho. Oh, we've seen rho before, but this is a different rho. This is a rho called resistivity. Resistivity, and that's material dependent. So this is where the material comes into play, your resistivity. Copper is always going to have the same resistivity. Gold will have the same resistivity. Tungsten will have the same. It's different from each one, but the same for any pure copper or gold or tungsten material. So that's your material. Here is your length, L. I had the capital L up there. They do little l here. And divided by cross-sectional area. They don't bring temperature into account because that can vary, okay? Because it's going to be hotter when it's been on a while, cooler when it isn't. So it's really hard to say what that's going to do to resistance. There are other formulas that will give you that, but let's just deal with that. So this is your formula for resistance, okay? So this is your cross-sectional area. This is your length, and this is your cross-sectional area, okay? So let's do example 1 then. Find the resistance, that's looking for R, of a copper wire. So we know it's copper, okay? Cu is for copper. 20 meters in length, so here's the length of 20.0 meters. Now that's a long wire, so you expect to have a fair amount of resistance. Copper is a good conductor, but it's that's a pretty long wire, okay? With a cross-sectional area, I probably should do this somewhere else. Let me, because I'm looking ahead and they're going to make some things a little more complicated for us. So the rho will depend on the material, copper. The length is 20.0 meters. That's a long wire. That's about 25 yards on a football field, you know, a quarter of a football field. Okay? I've lost it. There it is. Okay. With a cross-sectional area of, so your area here is 6.56 times 10 to the minus 3, and that will be square centimeters. This is why we had to do it off to the side. Okay, at 20 degrees Celsius. Okay, there's your temperature. That's your temperature, capital T. Okay, that doesn't enter the formula here. Okay, the resistivity of copper, so that's your rho, is equal to, at 20 degrees, so this resistivity at 20 degrees. So this is why we needed to know that. The wire is at 20 degrees. This is your resistivity at 20 degrees. So that's going to be fixed for us. Is 1.72 times 10 to the minus 6. Okay, the units here are ohm centimeters. Oh, and by the way, we didn't talk about the units for resistance, did we? All right. Now, it's on the next page you'll run into this guy, and his name is Georg Simon Ohm, O-H-M, okay? Now, he did a lot of the early studies. He came up with the fact that the current, the voltage is proportional to the current in a given material, and what is that constant proportionality? It turned out being the resistance of the material, okay? So he came up with that formula, and that's what we're going to do next, Ohm's law. And because he worked with resistance and defined resistance and stuff, they decided to name the unit of resistance after him. His name was ohm. So you would think maybe the unit would be capital O, right? That was his last name. Well, make up a number for resistance for me. 3. So what if we had 3 ohms? What's the problem with that? Look at that. I wrote it down. 3 ohms. Yeah, how can you tell if that's a 0 or an O? You have to be awfully good eye, especially with my writing. You had no way. That's why I slash my zero, so I'll know that's a zero. That would be confusing. So they say we can't use O. Well, what else can we do? We want to name it it's named after him, Ohm. So what do? Well, they went to the Greek alphabet. We've done that before. Remember micrometer? We already had used little m for millimeter, so for micrometer, we went to the Greek alphabet and did the mu. Okay? Just like we did, rho here is from the Greek alphabet. So let's go to the Greek alphabet and use a capital Omicron is the letter in the Greek alphabet for our letter O. So that would be 3 Omicron. Hey, it's the same symbol. We haven't gotten any better. But fortunately, Jasmine's here. Okay, good class tonight. Okay, so they went to the Greek alphabet. Fortunately, in the Greek alphabet, there's actually 2 letters that begin with O. The one that follows mu and nu, like our M and N, O, that's Omicron. That doesn't work. But the very last letter in the Greek alphabet, anyone know what it is? You probably will once I tell you the mnemonic device for it. It's what? No, actually, it's not. They don't have a Z like we do. Their last letter is omega. Now, some of you have probably heard this. Have you ever heard this? It's in Scripture. I am the Alpha and the Omega. You know what that means? The first and the last, the beginning and the end. The first letter in the Greek alphabet is Alpha. The last letter is Omega. The beginning and the end, the first and the last. We're on page 464 and 5, somewhere around there. 464 right now. So they use that. That's why they have. That's a capital Omega is that symbol there, and that's why we use it. Because it's named after Ohm, but they couldn't use a capital O or a capital Omicron, but they did use a capital Omega. Now the lowercase omega, I think we've seen before too, that's like that. It looks like a W, but it's not. That's an omega, lowercase omega. A W is usually pointed at the ends. These are curved like that, okay? Now, this is another really dumb thing. You don't need to know this, but the reciprocal of resistance is conductance. Resistance is how it opposes the flow of the current. Conductance is how easily it does. So they have a symbol called conductance, and they didn't really have a letter to represent it. So since conductance is equal to 1 over resistance, what letter could they use for conductance? Well, they couldn't use C. So many things are already using C. Huh? K? No, they use K for Coulomb's constant. You know, there were just so many places they've used K. So they needed some symbol for it. Oh, this just shows how sick physicists think, you know? Here's the symbol they use for it. Oh, first, what would they name the unit? They needed a name for it, and nobody really came up with it. Several people, lots of people did, so they needed a name for it. So what could they call the inverse of resistance? Where resistance was an ohm, what could they call the inverse of that? They called it a mo. Now, where did they get mo? How did they get mo? Yeah, they spelled ohm backwards. Boy. Exactly. You're thinking well. There was no, it wasn't Larry Moe and Curly who came up with it. That wasn't that. They just spelled ohm backwards. So what symbol do they use for a mo? They can't use M. They've already got meters. They've got millimeters. They got all sorts of things with M. So they can't use that. What would they use for a mo? Put on your thinking hat again. Here's what they came up with. They flipped the omega upside down. That's no letter in anybody's alphabet, but they just did the reciprocal of an omega, which was a mo. Okay, that just shows how sick physicists think. Okay.
When you make up stuff, you can make it up.
Yeah, why not? Okay, so anyway, that's not important for this class, but I just thought you might need to know a good trivia question. Whoa, my eraser didn't come up. Okay, so you don't need to know that, but it's out there for posterity. Okay, but you do need to know that omega is a symbol for resistance, named after, well, for the unit is an ohm, named after Georg Simon Ohm. Okay, we'll get to him a little bit later, but that's where the symbol omega comes from. So going back to resistance, which will be measured in ohms, we'll see, it's the conductivity, it's the resistivity at 20 degrees Celsius, so that's where the 20 degrees Celsius came from, 1.72 times 10 to the minus 6 ohm centimeters. Oh, we got a problem, don't we, Houston? Here we have centimeters, there we have centimeters, but up there we have the length in meters. We've got to change those meters to centimeters. So what we're going to do is multiply by our conversion factor, and we want this in centimeters, not meters. So which unit goes where? One goes above the line, one goes below the line. Which goes where? Meters go below, and centimeters go above. That way the meters cancel out. Perfect. How many centimeters in a meter, or how many meters in a centimeter? 100, which one? 100 centimeters is exactly 1 meter. Absolutely. 100 cents in a dollar, right? Cents? Okay, centi. Okay. So this makes it, and they put it in scientific notation, this would be 2 to 10 times 10 to the first times 10 to the second. So that'd be 2.0 times 10 to, actually 0 times 10 to the third centimeters. Okay? So, it's 2.00 times 10 to the third. I had to put the 2 zeros in there because, you see, this is 3 significant digits, so I need to get 3 there too. And that would be centimeters. So there's a length, 2 times 10, 2.00 times 10 to the third centimeters. Now the centimeters match, divided by the area, and that was 6.56 times 10 to the minus 3 centimeters squared. Okay? Now, notice what's happening here. These 2 centimeters cancel out those 2 centimeters, and that leaves us just ohm. That's what we measure resistance in. So our units work out. That's a good sign. Let's get the numbers to work out too. So on your calculator, it's 1.72. Now remember to do your scientific notation. You hit the key that's either EE or EXP. Don't put a times 10. Do EE or EXP, and then you'll get a little block come up, and then put -6. Now that negative is the negative sign in parentheses, not the subtraction key. You have to make a distinction there. Okay? Times 2, you don't have to put the 0, EE or EXP 3, divided by 5.6, I can't read, 6.56 EE or EXP minus 3. That minus in parentheses 3. Okay?
Times the 10.
You don't need, if you're using those keys, the EXP or EE key, don't use your times 10. That's the shortcut, to use the EE or EXP. Otherwise, it's probably going to be a pain in the neck or some other body part. Okay.
-3.
Yeah, -3. So what do you get for your resistance?
5.24
Times 10 to the?
12.
Okay. No, just 5.24, isn't it? It comes out that exactly. 5.24 ohms. Now, is that what you got? No, it's 0.254, isn't it? Yeah, 0.524 ohms. I was looking at the book. Here's how you know that. Okay. When you're multiplying exponents, exponential forms, you add the exponent. So this is a -6 plus 3. That gives you a -3. When you're dividing, you subtract. Well, -3 divided by -3 is 1. So that they go away. So those go away. Well, this comes out 2 times 1.72. That would be 3.48 divided by this. That's a little bit greater than 0.5. So yeah, it's 0.524. Okay. Or this may be what your calculator said. It may have said 5.24 times 10 to the first. And if it said that, or EE or AXP 1, that means, no, I'm sorry, to the -1. To the -1. And that means you move your decimal one place to the left, and that's your answer. 0.524 ohms. All right, that finished 17.5. Probably took too long on that. Sorry about that. You can do any of the odd number problems 1 through 9. Those answers should be in the back of the book. All right. Now, I've already been hinting around at, let me erase this, at Ohm's law. Okay? Yeah, we're not going to have a test tonight, so we're not going to finish the chapter. Is that why you stopped?
Yeah, and I was going to ask you about, will you email us or something and let us know which video to watch for this?
Okay, well, listen to tonight. At the end of tonight, before I shut down, I'll go to and show you which videos to watch. Okay, so go to the YouTube video for tonight. Okay. Now, this won't be up until sometime tomorrow, probably. Yeah. Yeah. Okay. In fact, sometimes it's late in the afternoon before they get back up. If I can get it to load tonight, I'll put it up there tonight. But sometimes, of course, it does nothing when I'm driving home. But if I get my computer out and get it working, our system at home is a little slow sometimes, so it may take a while for it to upload. And I may forget to do it too, so it depends on what the boss has in mind. All right, so 17.6 is talking about Ohm's law. And again, Georg Simon Ohm. That looks like George, but in German they say that. Actually, he was born in Bavaria, which is, yeah, that's part of Germany. Okay, that's Munich area. Okay. And he came up with this relationship, and it's called Ohm's law. Like I said, he determined that in many materials, not in all materials, but in many materials, the current is proportional to the voltage, or the voltage is proportional to the current. And that is then a Ohm's law. Okay? So if you put the current on the vertical axis and the voltage on the horizontal axis, and you get a straight line here. I should go through the origin, mine didn't. The slope here, rise over run, is 1 over the resistance. Okay? That is how they're related. So, so anyway, that's a rather awkward way of saying it. A little bit better way of saying it, well, another way of saying it is this. Symbolically, you have a resistor here. Remember, that's what a resistance looks like. You do a voltage across that resistance. That's your voltage. Okay? And you have a current moving through the resistance. That's your I. This is your resistor. There, you have V is equal to IR. That's one way of expressing Ohm's law. Actually, they express it differently in the book. They say I is equal to V over R. And that's where your I is equal to 1 over R times V. So that's where that comes from. That's why they did it that way. So there's actually 3 ways to express Ohm's law. I've just given you 2 of them. Can someone come up with the third one? I solved it for I solved it for V. The one R is equal to V over I. Divide both sides by I. and R is equal to V over I. Or you could do your circle or your triangle. I sort of like the triangle better, okay? And you put the one that's by itself, the V, or the one that's on top, the V, and put I and R down here, and then cover the V, and you got V is equal to I times R. That's this one. Then cover the I, and you get I is equal to V over R. Cover the R, and you got R is equal to V over I. Okay? 3 ways to express Ohm's law. All right. I, of course, is the current. What is that measured in? Louis ampere, measured in amps. Voltage is measured in. That's also potential difference, if you want to call it that. That is measured in volts. The symbol and the units are the same, capital V. And resistance this is resistance. And what's that measured in? Ohms. Ohm. Okay. You got it? Okay. So 3 different ways you can express that. Ohm's law. Okay. The one they do is basically this one. Okay. Ohms is volts divided by amps. Okay, but any one of the 3. Now they have a little activity here, and this is called, and they say, a string of lights. Now I bet you've run into this before too. We set up a little, very small greenhouse in our backyard, because my wife loves ferns and all these things to put out in the summertime. But in the wintertime, we didn't have any place to store them. Now, her lemon trees and her lime tree, she wants in the garage, okay, because that's a little bit warmer. But, you know, didn't have room for the ferns, so that means every year we're going to have to buy new ferns. I don't like spending that much money. She doesn't either, too much, but I like it a lot less than she does, okay. So, we decided to do a little greenhouse. But we needed something to warm it up. Now, we could take a little heater and put out there, but that was a little, but we found out, Karen read it somewhere, the old style Christmas lights that people don't like to use anymore because they got too hot and would dry out the tree too fast. People use LED lights now and other things like this. So we ask around my brothers and sisters-in-law and stuff like this, do you have any of the old-style Christmas? Oh, yeah, we have some. Where you go? Well, I was going to throw them away. Well, can we have them? So we strung those all over the greenhouse, and we plug those in, and they produce heat, and that keeps the thing. Well, I found out if I put more than 2 strings of those together, they use so much they blew a fuse.
I was about to say you catch on fire.
Yeah.
Well, no, but there's nothing in there to catch on fire, and I move them far apart. And in cold nights, that's the only time I turn them on. When it gets below freezing, then I turn on those, and it's cool enough that keeps them from catching on fire. And I turn them off in the morning or she does before we leave. Okay, so I don't know if that's what they were talking about, but that's what I said about string of lights. So let's do example 1 on page 466. I'm having trouble. My cataract in I already had a cataract replaced in my right eye, but they put a lens in there that was good for long vision, so now I don't have to wear glasses to drive anymore. But the cataract in this eye, the left eye, that was the one that was still okay for reading. It's gotten a lot worse, so I'm having more trouble reading, so I went to the doctor a couple weeks ago, and he scheduled me for cataract surgery in June. So in June, I'll be getting this one fixed. Hopefully, then I'll be able to read a little bit better. So I'm straining now. Okay, a heating element. Let's go to a new slide here. Can I erase this? Y'all got it? Okay. All right. A heating element on an electric range operating on a 240 volt circuit. That makes sense. That's pretty common. This is AC, by the way. We haven't talked about that yet, but this is AC. So the voltage here is 240 volts. Remember, this is the one that the parameter and the unit are the same, okay? All right. Now, in the book, and this is what I was afraid they do, they call that E rather than V. I guess to keep from getting confusing, but then it's so easy to confuse that with energy. It's not energy, it's energy per volt. I mean, energy per charge, or volts per coulomb, or joules per coulomb. So that's why I don't like to use it, but the book does, so I'll use it. Okay. Has a resistance of 30 ohms. So the resistance of this heating element is 30.0 ohms. Now that really, I'm surprised it's that low. What current does it draw? So we're looking for I. What would I be? From one of our three formulas? What is current? Voltage divided by resistance. So we do 240 volts divided by 30 ohms, okay? I'll cancel out the zeros there. I just divided by 10. Then 3 will go into 24 8 times. So that's going to be 8.0. And I can't tell that first one only is 2 digits. So 8.0. What unit for current? Amps. 8.0 amps. Yes, that's what they got to. Good for them. Okay. All right. Does that make sense? Okay. Example 2, let's see, I think we can do this one too. A flashlight bulb is connected to 2 dry cells. That means it's DC, direct current, and these are always much smaller voltages. 240 volts, that's got to be AC. You never get that many volts from dry cell unless you got an awful lot of batteries done end to end to end to end. Okay. So a flashlight bulb is connected to 2 dry cells with an equivalent voltage of, so your E, they're calling E, is 3.0 volts. That's typical of batteries. Now, your little 9-volt batteries, those are 9 volts, but that's about as much as you run into. Well, your car batteries are usually about 12 volts, okay? And if, I don't think we ever had a tractor that big, but one of the neighbors had a really big heavy-duty tractor, so it took a lot of voltage to start its motor engine, motor running. So they had 2 12-volt batteries back to back, so that was a 24-volt battery. I've heard some bulldozers and things like this actually have 36, but that's about as high as I ever see direct current going. Okay, so this is 3.0 volts. If it draws 15 milliamps, what's that a measure of? Say again? Yeah. What you measure in amps or milliamps? Not voltage. Voltage is in volts. No, resistance is in ohms. What's left?
Oh,
I, current. And that is 15 milliamps. Now there's a unit, so we need to get that into scientific notation. That would be 15, and what does milli stand for? -3. Okay. Now that's not quite in scientific notation, but we can deal with it. Okay? What is the resistance? That's what we're looking for, R. And what is that in terms of our Ohm's law? E over I. Perfect. So this will be 3.0 volts divided by 15 times 10 to the -3 amps. Okay? Now, I'm going to do some maneuvering here. Well, you can do it on your calculator. 3 divided by 15 EE or EXP -3. $200 ohms. Okay? What is the resistance? 200 ohms. Now, they make a special point of putting a line over that middle, the first zero, because you see this is only 2 significant digits. That's only 2 significant digits. So the first zero is significant. The second one is not. Okay. So that's why they put the line over it. Very good. Y'all are good at this. So that's Ohm's law, and that's 17.6. You can do any of these problems, the odd ones, 1 through 15, I believe it is. All right. Now, let's go back to the slide that we had before. So I'm going to get out of this one and go back to these pathetic little slides that the book has. And we talked about this one before. Now we're going to talk about this in terms of what kind of circuit it is. This is what we call a series circuit. Now this has no option but to be a series circuit. But what a series circuit means is that the same current flows through every wire in every element. So whatever current comes out of this goes through here, comes through here, as long as that switch is closed, and then goes back here. That is, these things are connected in series. If everything has to flow through, it only has one path. That's a series circuit. And this is how you illustrate that. The voltage source up here, the long bar on the plus side, the short bar on the minus side, and sometimes they'll put different number of bars to indicate how many cells that battery has. Okay, this would probably be 1.5 if they're doing it that way, or sometimes 2. Yeah, this depends, but most of the time they'll tell you. This is your load. Now that's not your typical symbol for load. We'll show that later. Your switch is like this. Right now it's open, no current's going through. Once you close it, then you get current through, and that's a series circuit because the same current goes through this. Remember, the load doesn't use current, it uses the energy from the charges. The current is the amount of charges per second. The voltage drop is the amount of energy being used per charge. Okay? So this is your very simplest series circuit. Now let's see if they show this. No, they don't. Okay? So on here, I'll show you the circuit diagram. They kind of did it here, but they did a really poor job of it. And for some reason, they reversed the sign of the battery. It doesn't really matter. Let me get my pen back. Okay. Didn't come back. There we go. All right. Now, for some reason, they reverse it and do it this way. It doesn't matter. Okay. That's the voltage source, or your battery. Okay. And then somewhere down here is the switch, just like they had here. Okay. But here's how you indicate a resistor. I did this earlier. A jagged line means that's a resistance. Excuse me. Okay. This would be your voltage or your E. Okay. This will be your resistance or your R. And your current would be what's flowing this way. So that's how we indicate the circuit diagram, we call it. Now, sorry, I've got such a bad case of hiccups. Okay. That's not coming up for a while. Sorry. I'm going to draw the series circuit they have on the bottom here. Oh, man. Doesn't matter where you put the elements. Here they're putting the battery here. Now this time they're indicating a 2-cell battery. Not that it really matters, but that's your E. Oh, sorry. And then it's going through one resistor, then through another resistor, then through another resistor before it goes back to the battery. So this would be R1, R2, and R3. They may not be the same sizes, the key here for this to be a series circuit is that the same current flows through each resistor. Okay? Because there's only one pathway there. It's got to go that way. Remember, the resistors don't use the current, they use the energy from the current. The battery supplies, sorry about that, supplies the charges with energy, joules per coulomb, and the resistors use up that energy. Okay. Now, you could take a voltmeter and place a cross here and measure the voltage across 1. You could measure the voltage across 2. And you could measure the voltage across 3. And guess what? These 3 voltages that you measure here have to add up to the total voltage in that the battery supplied. Because the battery is boosting the energy, the resistors are using it up. So this is a positive E here, and these are minus V's there, and they have to add up to 0. Because the same amount given is the same amount used. You can't create or destroy energy. You either use it or it's not provided. You know, I mean, it's got to be the same. The current, however, is the same throughout. The current through 1 is equal to the current through 2, is equal to the current through 3, because it's the same current flowing all the way through the circuit. Resistors may be different, okay? And that's fine. If they're different, the current's the same, so it'll have different voltage drops. If R1 was less than R2, then more current will go through that because there's less resistance, okay? And you'll have a lower voltage. No, I've said it backwards. The same current goes through all 3. The voltage drop across the first one, if that's a lower resistance, that'll be a lesser voltage drop, okay? If R2 is a medium, then you'll have a medium type voltage drop across it. If R3 is the biggest one, then you'll have the greatest voltage drop across that. Now I'm so sorry. So, the key here in a series circuit, I1 is equal to I2 is equal to I3, and so on and so on and so on. As many resistors as you have, it keeps going. Okay? The voltages add too. The voltage supplied by the battery is equal to voltage drop across 1 plus the voltage drop across 2 plus the voltage drop across 3 plus ... as many resistors as you have there. And the total resistance of the whole circuit, the resistance 1 plus resistance 2 plus resistance 3 plus ... Okay? So it's just like those 3, if you had one big resistor, that was the sum of the other 3, be the same thing. So the resistors add that way too. The currents, however, is the same across all of them. But the voltage supplied by the battery is equal to the voltage drop across each resistor. That's in a series circuit. Those are the laws in the series circuit. We call this the equivalent resistance. I sometimes will put R sub E. Some books will put R sub T, meaning total resistance. Actually, equivalent resistance is a little better because total makes you think they're always added. When we get to parallel circuits, which are different from these, they're not added, so you don't think of them as being total anymore. But it is equivalent. Okay. Now, and this is equal to the total current in the thing, because they're all the same. All right, let's do example 1. Sorry, oops, I didn't mean to do that. Hiccup, but change the slide. Okay. I'm going to erase some of this just because we don't have a lot of room to work with. But remember it, y'all got it written down somewhere. Okay. Oh, I didn't mean to do that. I'll erase this one down here. That'll give us a lot more room. Okay. I'm so sorry. If we had more time, I'd go out and get a long, slow drink of water and try to get rid of these things. But I don't. It says, find the total resistance, example 1, bottom of page 469. Find the total resistance of the circuit shown in figure 1728. So I'll show this here. R1. Now, they don't show these individual voltages, so I'll erase them too. Still true, but I'll erase it. And they don't even care about the current, but I think I'll leave that. If I have room for it, I'll leave it. So I should have left one of my formulas up there. R1 is 7.00 ohms. R2 is 9.00 ohms. And R3 is 21.0 ohms. All three have three significant digits. They're not asking for anything else except what is the equivalent resistance, which they usually just call R. I like to call R sub E. What would it be on this series circuit? I like to do that one first. Second?
7.0.
No, what's the... No, the resistance add. So add up the three resistors.
Oh.
37.0
Yeah.
ohms. Three significant digits.
Oh,
Yeah.
too simple.
The current remains the same through all of them, whatever it was. They didn't even give us the current. If they had given us the voltage, we could have calculated the current. If they had given us the current, we could have calculated the voltage. But they only gave us three resistors. That's all we can calculate here. Unless, of course, the next example says to do something else. Nope. No, it's a different one. So I was thinking they would be smart if they did the same and just ask us to calculate the next thing. But now I've got my pen all tangled up with my wire. And still hiccuping. All right. Example 2, they say find the current. Okay, let me erase what I need to erase here. R1 is different. R2 is different. R3 is different. Okay. Oh, and they put a R4 in here, which is a shame, because I have to draw that in. Okay. They put another resistor in series with the others, because there's only one pathway. This will be R4, and R4 is 96 ohms. Okay. R1 here is 5 ohms. R2 here is 13 ohms. And R3 here is 12 ohms. Oh, and this time they told us what E was. E is 90 volts. And the question is, what is I? Now, which I is that? It's a series circuit. It's the same I everywhere. So it's any one of the I. They're all the same, because this is a series circuit. The same current throws through everything. Okay, how can we calculate the I? That's what they're asking for. Find the current in this circuit. Yes, first calculate the, oh, I didn't erase that, did I? Let me not confuse the issue here. Okay. All right, pulled out the calculator and going to town here. Well, 12 and 13 are 25, and 5 is 30, and 96 would be 126, right? So this would be 126, and we don't need the 0.0 because those are our three significant digits right there. Okay, 126 ohms. All right, what can we do with that?
The only thing you got left is the 90.
Okay, so what is I? This is total or equivalent resistance. So what is I? What? Huh? What's always on top? V over R. Okay? So that would be 90. I can't write. I say 90 and write 9. What is wrong with this picture? Okay. Let's try that again. 90.0 volts divided by 126. Oh, I didn't put unit. Oh, yeah, I do. There it is. Ohms. Pull out the calculator, see what you get. It's about maybe 0.3 or so. Maybe upper 0.2. 0.71. Yeah, 0.7. Okay. So again, 0.714. What unit? Second? Amps. Amps. Okay.
You seem like it.
Okay. Now, if you don't like decimals, you could do 3 digits that way and make it 714 milliamps. I just as soon have 0.714 amps. But either answer is perfectly fine and correct at that. 0.714 amps. Very good. Now, what they didn't ask you, but you could easily calculate, what's the voltage drop across each resistor? We know that because E is equal to I times R. Well, you got your I, 0.714 amps. Multiply that by 5. That would give you the voltage drop across R1. Multiply the 0.714 times 13. That would give you R2. Multiply it by 12. You get R3. Multiply it by 96. You get R4. You get V4. Add those up. You get awfully close to 90. You may not get exactly because you have some round off error there, but you'll get awfully close. Okay. They didn't ask us to. We're not going to do it, but we could have. Now let's do, can I erase this? Y'all got it? Okay. Do I erase it all? No, let's just erase some of it. Okay, let's erase it all. Find the value R3 in the circuit shown in figure 1730. Okay. Here is the figure 1730. Again, they show a battery. They show 2 cells. It doesn't have to be. Actually, that's not a battery. It looks like a battery. And this is going through R1. It's going through R2. It's going through R3, and it goes back to the battery. The reason I say it's not a battery, they say the E here is equal to 115 volts. That would be one big battery. This is alternating current. You're plugged into the wall here. That's very typical of circuit voltage in a house or a building, 115 volts. Okay? You have the R1 up here, which they tell you is 23.0 ohms. You have the R2 over here, which they tell you is 14.0 ohms. And they have R3 down here that they don't tell you anything about it. But they also tell you that you have a current here. I've got to sneeze. And that's y'all awake yet? Okay, good. Whew. This current, they tell you, is 3.00 amps. I can't write. That's an A for amps. It's awfully crowded up there. Okay. And they're asking you, what is R3? How in the world are we going to get that?
You gotta do the first two first, like the R1 and R2.
Okay. The thing is, the resistances we're not sure about because we don't know R3. But we know the voltage and we know the current. So we know the total resistance of the circuit, and then we can figure out what R3 is, right? So how do we do that? The R total is equal to Ohm's law. No. V over R, E over R. I mean V over I. Okay. Voltage is always on top in Ohm's law. Okay. If you have a top, voltage is up there. Get your little triangle down. V's on top. Okay. Or your circle if you prefer the circle. Okay. So what's your E? 115 volts. What's your I? Hickey up. 3.00 amps. So figure out what R is. Sorry. Gonna be a weird number. 38.3. We'll just leave it at 0.3 now because that's all the digits we have. And that would be what unit? Ohms. Okay. We know the first two add up to be,
Oh, I'm sorry.
37 ohms. So what does that leave R3 to be? The total is 38.3. The sum of R1 and R2 is 37. Say again? Don't you subtract here? The difference would be 1.3 ohms. That's awfully small. Yep, that's what they got. 1.3 ohms. Now, if any of you are worried about, wait, there's only two significant digits there, okay? When you add or subtract, you don't use significant digits, you use the nearest, this was to the nearest tenth, that's to the nearest tenth. You can only go to the nearest tenth. So you don't have three significant digits there, you only have two. Only in multiplying and dividing do you have to keep up with the number of digits. Adding or subtracting, you go with whatever you got. Okay. Sorry. Now, this is where I'm glad I didn't erase. Okay? Because it says find the voltage drop across R3 in this example 3. Okay, how can you find the V3, the voltage drop across that resistor? No, V is equal to the third one that we haven't used yet, but it's, to me, the basic one. No, this is voltage. Ohm's law. What's the third one? So, see, V is the one on top, so what these down here are multiplied. What are the two down here? Say again? What's your three parameters? Voltage, current, and resistance. So what are the two at the bottom? Yeah, current and resistance. I times R. And we know what I is, don't we? It's the same current throughout the whole circuit here. So this is, sorry, 3.00 amps multiplied by 1.3 ohms, only two single digits there, so your answer is now going to drop to only two single digits. On your calculator, that's going to be 3.9 what? Volts. Perfect. And that's what they got to. Good for them. Okay, is that making sense? All right, here's sort of a summary slide then. Okay, I've already had this on the board once. I've written it, but now they're writing it. In a series circuit, remember this series circuit, that's going to be current is the same throughout the circuit. Your total current is your first current, is your second current, is your third. They're all the same. It's one current, okay, throughout the circuit because there's only one pathway. You can't lose or gain current. It's going to be the same. Your resistances, however, add. It's just like all these little resistors add to be one big resistor. Okay? The voltage that you supply by the battery or you plug in the wall, that is going to be the voltage drop across each resistor. Because that which you add is used up and by all the resistors. So there is your summary of series circuits. All right? Which then leads us to the problem set, 17.7, which you can do any of the odds. I'd probably break these up 1 through 5, and then do any of the odds 7 through 9, and then 11, and or 13, or however you want to do those. All right. I don't think we're going to have time for parallel circuits tonight, so we will stop there. Somewhere I did have a pencil. We'll stop and pick up with parallel circuits next time.
I have a question.
Yes.
I'm just trying to make sure all the numbers on questions on number 7 for the, I think it's the 4th test, are those right? Because I'm coming up
Okay.
with some kind of,
Let me see which one you're talking about. What is the first question on it?
the first question, find the period of wave through frequency.
Find the what?
The period of wave.
Okay, wait, okay. Find period of wave. Okay, all right.
Number 7,
And which one are you talking about?
Number 7.
Number 7.
Because I'm getting a weird little number, but it could be right.
Okay. Okay, when it says, how long will it take a wave to propagate or travel through 150 meters at 25 degrees Celsius? Okay, now, oh, a sound wave. I left off that, a sound wave. Okay, now, if you got to go, be sure to listen to the video to see which ones to listen to for next week. But if you can wait, I'll be doing that in just a minute. They didn't say, oh yeah, they did say at 25 degrees. So if you go back to, this is in chapter 16, right? Okay, go back to speed of sound in various media, and, is this at water?
I don't know. Don't say.
Let's assume it's air. So let's go to, wait. I turned too far. Okay.
Maybe water with the 25.
No, sound waves, yeah. Here's what you use, yeah.
What page?
On page 436, your velocity you get from that first equation in the green box. V is equal to 331 meters per second plus 0.61 meters per second per degree Celsius times 25 degrees Celsius. You multiply that, and that gives you your velocity. Okay? Then once you know the velocity, here's the distance. You can calculate time.
Okay.
Velocity equal distance divided by time.
All right.
There's your formula. Okay. All right. Now we finished through, today, we finished through 17.7. So what I'm going to do, I'm going to end this. Oh, no, I'm not going to end it. What am I going to do? Let's discard. Okay. Now, what I need to do, sorry if this is going to take a little longer than what it probably should. Let's go to YouTube. Oops. What's that? Yeah, I believe so. I just was there. I think I had an extra one. That was the one that we were just talking about, right? Yep, right there. The only reason I'm being lazy and sitting here is because I'm waiting for this to come up. Yeah, but let me give you, I think you can read it, but just in case you can't. Oh, it's finally coming up. Whoa, went too far. Here we go. Okay, number 8 and 9, they forgot to give you the frequencies of the whistles or the other thing. But I've written it there. 585 hertz, okay, is number 8, and 5,000 hertz is number 9.
Okay.
Okay.
Thank you.
Okay, now, it's slowly getting here. Here we go. YouTube videos. All right. What is this? I don't know what that is, but I'm going to get rid of it. Okay, I'm going to sign in here. Sorry, this is taking a little bit of time. I probably could have gone through Blackboard and gotten there just about it. No, Blackboard's slow too, so let's see. Okay. Okay, now we'll go to my channel. Okay. Now, y'all don't have to do all this because I have a bunch of these. You only have a few. There's physical. That's physical science, not physics. Okay, let's go to physics 112. Okay. Now, when you get there, this is what you see. You'll see 19, 1, 2, 4, yeah, all those at the top. Then you'll see 17. Ignore those. We haven't gotten there yet. On okay, wait. Let's just go over now. Or, let's see. Okay. Why don't y'all stop me before anyone has to go? That'll allow more people to come in, and that way I won't be repeating everything several times. So, tonight we did 17. If anyone has to leave early, stop me at least a few minutes before you have to go, so I can go over how we're going to wrap up the term. Okay.
5.
And we got through 17.7. Okay. So that will, I'll erase this one once I load the new one. And I'll leave this one up there. Now some of that we've already done. The last part of 17.6 we've already done. No,
I forgot something.
Yeah, the last part of 17.6, but we haven't done any in 17.8 yet.
Oh,
so if you watch
huge gap
all of this one and all of this one, 17,
so let's get started on this
6 and 8, and 8 and 9. And
first,
then
any
next
questions
time
on anything we've done
we'll
so
start.
All right.
Where we're beginning today is 18.4, And the
Something
title of this is
sort
an
of backwards
induced
here.
current. And let me just remind you so you can remind me.
All right. I don't know why it's like this, but if
You don't
I'm
have
going
to
to
do
leave
this.
up here,
We go from here to 18.7.
I'm going to delete, once I load the new
You
one,
really only
I'm going to
needed
delete 17, 3
18.1
through
and
6.
2. I did too much last
I'll leave
time.
up there
So
6
let's
and
move
through
to
8 and 8 through 9.
18.7.
This one will be there too. I don't know why
That was fun, though,
17.5
wasn't
is
it?
in with those other two, but that's sort of squirrely.
Actually, these are very short sections, so it
so-
doesn't take much.
But
do
you
that.
see, yours will be at the bottom down here. There was 17.5
Wow.
last time. We'll do
18.7 is
5 through 17.
less than a page.
Will be this time, and that will show up at the bottom. And then you go up here
So let's go back to the other
at
one.
the top, near the top, and you do. I'll take off the 17.3 to 6.
And let's see what
and
we've got there.
We'll do. I'll leave this one and that one. Those are the two you study for next week.
Okay.
Okay. This you already have a little bit of that 17.6 part. You'll do 7, 8.
That's on this.
No, 8 and
Okay.
9.
We do have a
So
slide
you
here.
do 8 and 9.
Now,
The 6 and 7 we've already done. You start at 8.
this may
and then
actually
do 8
be
and 9.
something
And then we'll pick up at
that
the end of 9.
I don't know.
Or
if
you tell me
have
where
to know
9
it to
left
know what
off
you're going to be doing.
when we meet in
but
2 weeks.
it might
and
really
that's
be
what we'll
helpful
pick up
to you.
next time. It looks
All
like maybe we did it all, that one, but I can't tell for sure. 9
This is
compound
talking
circuits.
specifically
If they
about
didn't finish
scans,
compound circuits, tell me where
which
it
is
left
what
off,
y'all are going to
and
be
that's where
doing.
we'll begin.
Now, y'all going to be doing mostly
weeks.
sonograms,
Okay.
or will you be other scan
All right, does that make
techniques
sense?
as well? For
All right.
instance, CT,
So I recorded that for
MRI, or-
everybody. So I'm
other
going to get out of
things.
here.
What's that?
All right. See you in 2 weeks. Sorry I have to be gone next week. I wouldn't mind driving back, but the people who got here early said don't do it, so you talked me out of it. Okay, great. Thank you. You already got 4, right?
Yes, sir.
Okay, great. Thank you so much.